G'day, Lance again from Motive Power. And today we're going to talk about making everything move in a controlled fashion. We're going to talk about gearboxes. Welcome back. As always, this is only guidance, it is not advice. It's information you may seek to search out further. So, as normal too, we're going to start with some terminology and talk about what sort of transmissions are readily available. Now, I'm not going to talk too much about hydraulic hydrostatic drives. Again, they're a topic for themselves, but we'll touch on the requirements for them anyway. So the first up is an automatic transmission. Probably got one in your car. Same deal in off-highway. It's just that they're a little bigger. Let's have a look at a quick picture. Allison are probably regarded as the largest manufacturer in the world. There's probably some Europeans that might disagree, but they can be awkward to deal with. This is a typical Allison automatic transmission, and it doesn't look too much different to what's on your car. You'll recognise it, an output at the back, a flywheel housing at the front, and a thing in the middle full of gears. What basically defines an automatic transmission is that it shifts the gears automatically. Sounds like a simple definition. The lines can be blurred a little bit, but essentially automatic transmission, just like in your car. Then we get power shift transmissions. This is a Dana Clark transmission. The actual technology inside them is very similar. Same sort of epicyclic gearbox of gear sets and clutches. They're made for different duties. Essentially, a power shift is not an automatic shifting transmission, although with the appropriate electronic box on it, it can become so. These are designed to be shifted by hand, and they shift under power, under load, hence power shift. In different versions, this one is what's called a long drop. The drive comes in, goes down, and can come out the bottom going to perhaps a front and rear axle. There are short drops available, and there's also essentially no drop. This is the controlling set of valves out the side. This particular one is set up for remote mounting. The input to it is via a drive shaft. It's not directly mounted or coupled to the engine. Of course, there's also the good old manual transmission, perhaps a Road Ranger. I don't like them. I've used them once and had problems. Generally on off-highway vehicles, my attitude is the operator's eyes should be outside looking at what's around. Off-highway vehicles are generally oversized. The application I had problems with was in a crane carrier, a big crane carrier. Big boom out the front, 3.3 metres wide. The driver's eyes needed to be outside, not looking down trying to work out what gear he's in and how to get to the right one. So you can use them, more conventional for lighter loads. And then more recently, continuously variable transmissions have become available. CVTs for short. If you imagine two pulleys with belt between them and those pulley diameters can vary, and thereby adjusting the ratio. It works really well on my Polaris Ranger, but I don't really like it in larger applications. I've driven Mitsubishis with CVTs and didn't like it. You come down an on-ramp to a freeway, you put your foot down to accelerate to freeway speed, the engine revs up, and sometime later the transmission catches up. Not ideal, but ideal for the right application. We'll also talk about drop boxes and transfer cases. Essentially, they're the same thing. If they drop the drive, they're a drop box. If they transfer it sideways, they're a transfer case. Minor differences between the two, maybe around lubrication, and of course, sometimes they can be used midway. They don't have to be vertical or horizontal. They can be in the middle. Let's have a quick look. So here's a fairly typical transfer case. As you see, it's called a transfer case. And lots of manufacturers have fairly standard ranges. There's some more options. Again, these are configured to be drop boxes where the drive is being dropped. And here's a typical sort of drawing of what's inside them. Inputs, gears, outputs. How many gears, how big the drop is perhaps an alternative. Whether there's a front axle disconnect, whether there's a drive through or just one single input flange. There's a variety of options. But essentially, that's a drop box or a transfer case. I'll say, so why do you have a gearbox? Well, it's actually to create torque, not power, torque. And that torque, of course, cascades down the drive line and hopefully comes out mostly at the wheels. Because engines work in a finite area of finite rev range, they can't cover the entire range of the vehicle speed. So you have to break it up into segments, and that's what a gearbox is about. They gear the engine down to an acceptable speed to drive the vehicle. Now, they don't need to be mounted on the back of the engine. So we've just seen with a Dana transmission, it can be mounted remotely with a drive shaft to it. But we could also put the torque converter on the engine and a drive shaft to the actual gearbox itself. That's also done. It's about packaging, particularly for low height vehicles. That's when that sort of broken up installation works best. Engines in most vehicles, like your car, are generally placed above an axle. It's just the way the packaging works. So when you try and squash that vehicle down to make it lower, there's only so much you can do because the engine hits the axle. So you move the engine to the side and have a drive shaft over the axle to a drop box or a transmission. That engine, and that's where remote mounts come in handy, whether you put the torque converter on the engine or leave it on the transmission. Somewhere in this drive line will also be drive shafts. Find a damn good supplier, make sure you've got the technical data from them. Trust but verify. In general terms, there's two types, a Spicer or Mechanics. It's a bit like whether you drive a Ford or a GM. It's personal preference. From a design point of view, I'm trying to use as many standard components as I can. I look at what options are available on the transmission, look at what's available on the drop box or the axles, and try and match them up. You can't have a Spicer on one end of a shaft and a Mechanics on the other. It doesn't work. You need to have the same type of joint on the one shaft. So ideally, the same sort of joint all the way through the vehicle. Get the data, work out the torques and all the rest of it, and make sure you select the right one. Of course, there's also CV joints, typically in a drive steer configuration, but not necessarily. A lot of big heavy vehicles don't have CV joints. They have double unis, two universals back to back, which closely approximates what you'll get out of a CV. The other thing to be aware of with a CV is, well, firstly, they're basically unrepairable, and secondly, they often require plunge. The actual working of the CV, the geometry of it, requires one of the shafts to plunge, to move in and out. You have to have room for that. That's particularly a situation with suspensions, independent suspension. The shaft from the CV will have to plunge at one end or the other. When you're installing them or designing the vehicle for these shafts to be installed, there's a real tendency, because it's easy, just draw them straight. Don't ever do that. That will cause the bearings to Brinell and the joints will fail. You need at least about 2.5 or 3 degrees in each joint. And that keeps the bearings working and everything happy. The other thing to watch is the maintenance on them. Drive shafts can be in some fairly awkward positions, and if you've got a type that needs to be greased regularly, that can be a problem. It may well be that it's never going to get greased. On the Ventrac tractor that you've seen me use earlier as an example, there's one grease nipple on a drive shaft that not only have I had to get a special hose for, I have a special side slide-on grease cup, and never knew they existed. That's the only thing that will get to that grease nipple. As a designer, you should be trying to design that sort of problem right out at the design stage. So a bit more about automatics versus power shifts. Power shifts often have as many reverses as they do forwards. So again, good for loaders, good for locomotives, and automatics are more optimized for going in the one direction, i.e. a big truck, although they may have a couple of reverse speeds. Whichever one you use, you're going to be back to the application forms that we've spoken about earlier. Again, fill them in. If you're using axles and transmissions from the one manufacturer, then you probably only need to do the application form once, and they'll do the transmission and axle selection for you. But they won't always ask you what sort of converter you want. It will pop out of their analysis and they'll just submit it to you. If you get into it, there are probably 3 different types of converters in terms of the way they work that you should be considering. Now, it basically comes down to where that converter will stall. My preference is what's called an outmatch, that the converter stalls at maximum torque, engine torque, so that you're getting the most grunt out of the engine, and the torque converter then of course multiplies it, which is the second reason for using a torque converter, and you get the best performance out of the vehicle. But that's not necessarily the best option for your application. It is good for vehicles operating as, for example, true loaders. And I say true because a lot of loaders get used as tool carriers. But if you are digging into a spoil pile and breaking out and carrying it off, you want the maximum grunt. So that's an outmatch. You want a less aggressive approach. A match called a lug match is typically used on forklifts. It makes them a little more drivable, but of course you're going to lose tractive effort. On a forklift in a warehouse, that probably doesn't matter, and it's more about drivability perhaps that means safety. What that means is the engine doesn't reach peak torque before the converter stalls. So you're not getting your maximum performance. It's better for drivability, but it also allows more creep, better control of creep. And if you think about a forklift coming up to a rack, you want them to be able to creep into place easily, safely. It's also good for, just reading my notes here, for hauling trailers or large loads, and provides the best tractive effort speed compromise. All engineering is a compromise. Most of the vehicles I've designed have been about maximum performance, and hence I've gone for outmatch. Drivability, perhaps you should consider a lug match. There's also a thing called a full match. It's used for telehandlers because they get used in so many different ways, and it's a compromise that seems to suit them best. It's not very often used. It stalls at a full power point, not full torque. Now, my notes say it's the best compromise if you're not certain how the vehicle's going to be used. I struggle with this one a bit. Why build a vehicle and then not get the most performance out of it? But sometimes there are other issues beyond drivetrain that push you this way. I'm aware of a client who likes a full match. He likes to, when the converter stalls, he likes that not only is the engine at full power RPM, but it's hopefully in governor droop. My suspicion is that that makes his statutory emissions tests easier to pass, because engines at peak power are more efficient than at peak torque, produce less emissions. And of course, if you go past peak power and you get into governor droop, where the fuel's being cut back further, that's even better. So there are different converter arrangements for different applications. You need to think about it. You need to talk to your suppliers. 30 plus years in the game before I realised that there were alternative converters. So quiz your rep, give him a hard time, find out what options he can provide. So when you do all of this application form and provide all that tech data, what will come back to you is a set of curves and a whole lot of data that's going to be good for you. You can work out from that what sort of transmission cooler you'll need, because it will tell you the heat rejection and where it's efficient, where it's not. Beyond that, as for engines, there's usually a wad of requirements, application engineering notes, for example. And it will cover things like bending moments on flywheels and what sort of harmonics are permissible, how to shift the gear. As you hopefully have tested your engine supplier to get hold of all of this data about engines, you now need to do the same for the transmission. A, when you know it, it's easier to design, and they're generally fairly easy instructions to follow. B, it's all about warranty. You're not building vehicles for the love of it. You're building vehicles to make money. Don't want warranty. So, again, fill in the paperwork, follow what's instructed, and sleep easily at night. So, these days, whether it's an automatic transmission or a power shift, there's generally going to be electronics either involved or available. Now, why is that important? Well, you can go to the full extent and send real-time data to some home base for analysis that generally nobody will ever look at. Or you can use it to tell the driver about the vehicle he's driving, whether it's hot or running at peak performance or needs a tune-up or whatever. or you can just plain straight out use it to get the best vehicle performance. So I'm going to show you an example where we did that. This is a Bliss Fox aircraft towing tractor, 54 tonne, towing in this case a test Airbus A380 at 545 tonne. So big beast, 2 computers on board, one for the engine, one for the transmission. And we didn't want to shock the plane. Very expensive, these things. Nobody likes them to be subjected to excessive load. So using the electronics in the transmission, we were able to do a couple of things to make a big difference. Number one, we programmed it so that the converter did not lock up. It stayed in its slippery state in first gear. Number two, first gear was manually selected. When you put it in drive, you did not get first. It started off in second. And number three, changing from 2 to 3, second to third gear, it shifted in governor droop. So that meant the revs had gone right up to peak power and started to come off, and that's when it would shift. Now that meant that we got a softer shift, and the equipment works fine, has worked fine for many years. So think about what the electronics can do for the vehicle operation. Not just the sexy stuff of having a glass cockpit or any of the other stuff. What's it actually doing back there in the engine bay that you need? And if it's not doing anything you need, get rid of it. Now, I use towing tractor application. In airports for that sort of equipment, there are a few requirements around electrics. Not much. You've got to have a rubber flap over the battery and a few other simple things. But it's all about not creating sparks that might ignite aviation fuel. In other applications, you get back to chemical refinery or chemical plants, oil refineries, coal mines, it's not so simple to use electrics. And in fact, if power shift transmissions are used, they don't have any electrics on them, and nobody uses an automatic. So some applications you won't be allowed to use the electrics. One of the trick bits in drivelines, particularly for vehicles that run on hard stand, is does it have an interaxle differential? Remember this drop box. This is driving, let's say, the rear axle. This is driving, say, the front axle. This has an optional front axle disconnect. But if you're driving on hard stand and you don't have a disconnect, and you may not, there's a valid reason for not having it, the front and rear axles are being driven at the same speed. If you're in four-wheel drive, four-wheel steer, that's not a problem. But if you want two-wheel steer, that is a problem because the speeds on the axles need to be different. And that's where an interaxle differential, right here, is important. Now, even if you think that you're always running on soft ground, where there'll be no crow hop, that the tyres just slip a little bit to make up the difference in the speeds, think again, because there's a fair chance that vehicle that always operates on hard ground, on soft ground, gets into a workshop or onto a road on occasions, somewhere where it can't work out the difference in speeds between axles. And you're either going to slip a tyre. In four-wheel drives on highway, it tends to be called crow hop. It'll hop a bit as it jerks and one tyre will spin. Back to those aircraft towing tractors. Their ballast is really heavy, so you don't get wheel spin. You can't really afford to have a wheel spinning because your performance will be seriously degraded. So the professional ones, the better ones, have interaxle differentials here. If you don't, you go down the path of some German tractors that simplify the design, a little bit cheaper, but wear tyres out quicker. So, having got an interaxle differential in there, the next question is, does it need to lock? And yeah, it might need to be a locker. Certainly if it's a Triton or a tandem, I'd recommend a locker, particularly in a Triton. But there's always the question of, will the operator remember to undo it, to unlock it when he gets back on good ground? It's not that simple. It almost needs a spike in the seat to get operators to remember. A little light on the dash, maybe. A flashing light with a buzzer, even better, but someone will stuff a rag in the buzzer or cut the wires. It's an operational problem, but it's something you need to consider at the design stage. Still on interaxle diffs. Again, that towing tractor had 3 diffs all around. Both axles had a free diff, an open diff, and one in the drop box. Ballasted up, 54 tonne or beyond, and then if one wheel spins, it will rob all the other wheels of torque. Remember, differential split torque 50-50. So if one wheel on that axle is running at half the torque of the other, then that other axle, that other wheel will also get half the torque. Big issue around diffs. You've got to be very careful about them. But interaxle diffs, you really just need to decide where you need the torque to flow and put your diff locks or not to suit. So that's a very quick overview. I haven't gone into how torque converters work and so forth. From a design point of view, a vehicle design point of view, you may not need to know all that stuff because your suppliers are taking care of the inner workings. Your job is to make sure that the outer stuff fits your vehicle and it works better. The transmissions do determine the performance and the drivability of the vehicle. So I again say to you, go through all the details, fill in the damn forms, and then you can sleep at night as the rest of the vehicle design continues.